Lightning bolts. Today, we're going to pull back the curtain on one of these forces, the unseen architect of just about everything, electrostatics.
And yeah, the answer is electrostatics. It's the science of electric charges that are just sitting still, not moving around. Now, the name might sound a little heavy, but the rules are actually surprisingly simple. And that's what we're going to do today. We're going to break down those rules to really understand how this force shapes our entire reality.
You know, every fundamental force in the universe has a sort of rule book it has to follow. No exceptions. For electrostatics, that rulebook kicks off with one single incredibly powerful law that tells you everything you need to know about the force between any two charges, anywhere.
And here it is. This is our first and honestly our most important building block, Coulomb's law. It gives us the exact strength of the push or the pull between two charged objects. It's the absolute foundation for everything we're about to get into.
Okay, so don't get spooked by the math here. I promise it's more intuitive than it looks. The force, F, gets bigger if the charges, Q1 and Q2, are bigger. That makes total sense. More charge means more force, more oomph. But the real game changer here is that R on the bottom, the distance. See how it's squared? That means the force gets weaker dramatically as things move apart. If you double the distance, you don't just cut the force in half, you slash it down to a quarter of what it was. This inverse square relationship is a huge deal. It's like a secret code you see all over physics.
So, while the formula tells us how much force there is, this super simple rule tells us which way it's going. Opposites attract, likes repel. It's that simple. And between the formula and this rule, you have the whole picture, how strong the force is and which way it's pointing.
Now, does that formula look a little familiar? It should. The structure is almost a dead ringer for the law of gravity. They both get weaker with distance in the exact same way. But here is the critical difference, and it changes everything. Gravity only attracts. It only pulls. Electrostatics can both push and pull. That one difference is what makes the electric world so incredibly dynamic and, on the atomic scale, just unbelievably stronger than gravity. So, calculating the force between two charges, pretty straightforward. But what about millions of charges? That would be a nightmare. So physicists came up with a really clever workaround. Instead of tracking every single interaction, they created a map of the potential force in any given area. And that's where the idea of an electric field comes from.
Just think of the electric field like a weather map, but for forces. It doesn't tell you the force on your specific charge. Instead, it shows you the force that would be felt by a standard, generic test charge if you dropped it at any point on the map. It's a brilliant way to visualize the influence a charge has on the empty space all around it.
And look at this. Notice how the formula for the electric field, E, comes directly from Coulomb's law. We're basically just defining the field as the force per unit of charge. So we just take our original force formula and divide out one of the Q's. It's a perfect example of how these concepts just neatly stack on top of each other, building a really logical and powerful framework.
Now, electric fields can get pretty messy and complicated, but there's a special case that is incredibly useful: the space between two parallel plates. In that little gap, the field is uniform. That means it has the same strength and direction absolutely everywhere. And this simplifies the math like you wouldn't believe. The field, E, is just the voltage, V, divided by the distance, D. This little shortcut is a super powerful tool, as we're about to see.
All right, so far we've been talking about forces and fields, all pushes and pulls. But now, let's shift our perspective a bit and talk about energy. I mean, if an electric field can push something, it must take work, it must take energy to move a charge against that push, right? Just like it takes energy to lift a book against gravity.
This brings us to electric potential, which you probably know by its more common name, voltage. The best way to think about it is like a hill. A point with high potential is like being at the top of the hill. It took energy to push a ball up there, and now that energy is stored, ready to go. It's the exact same idea here. It takes work to push a positive charge to a point of high electric potential.
So here's the formula for electric potential. Take a close look. It's really similar to the other formulas we've seen, but with one massive difference. R is not squared. This might seem like a tiny change, but it totally changes what we're measuring. And as we're about to find out, it makes our lives and our calculations way, way easier.
And this is the key. This is the big takeaway. Force in the electric field are vectors. That means they have a direction and angle you have to worry about, which can make the math messy. But electric potential? It's a scalar.
It's just a number. It has no direction. This means if you have multiple potentials, you can just add them up. No angles, no complicated vector math. It's a huge shortcut that simplifies even the most gnarly-looking problems.
Okay, we've got our toolkit, we've got force, we've got fields, and we've got potential. We know the difference between vectors and scalars, so now for the fun point. Let's put these tools to work and solve a classic physics problem to see how it all fits together in the real world. So here's the setup, straight from an old exam question. We've got a tiny, charged sphere, and it's placed between two metal plates. And the crucial piece of information is that it just floats. It hangs there, perfectly still, suspended in midair. So the question is, how is that even possible?
Well, Physics 101 tells us that if an object is stationary, all the forces acting on it have to be perfectly balanced. They have to cancel each other out. And we've got two forces in a tug-of-war here. First, you've got gravity, pulling the sphere down with a force equal to its weight. So for it to float, there has to be an equal and opposite force pushing it up. And that can only be one thing, the electrostatic force, which we know is its charge, Q, times the electric field, E.
And here is where all our building blocks just click into place. First, we set the forces equal to each other. Then we substitute the formulas we already know for each force. Then we use that awesome little shortcut for the uniform field between the plates. And suddenly we're left with a nice clean equation with only one thing we don't know, the charge, Q. A little bit of algebra and boom, we've got our answer. It's just a perfect example of how these fundamental ideas let us solve real problems. Okay, making a tiny sphere float is pretty cool, but that is definitely not the only trick electrostatics has up its sleeve. These same exact principles are at work deep inside the atom, letting us actually probe the secrets of the atomic nucleus itself. Picture this experiment. You take a positively charged alpha particle, and you fire it like a tiny cannonball straight at a positively charged nucleus. Now, because like charges repel, that alpha particle is going to slow down as it gets closer. Eventually, it will stop for just an instant and then get shoved straight back where it came from. That turnaround point is called the closest distance of approach.
What's happening here is a beautiful example of energy conservation. All the kinetic energy of the particle, its energy of motion, gets converted into stored potential energy as it fights against that repulsive electric field. And here's the genius part. By measuring exactly how close it gets before it turns around, we can work backwards to actually figure out the size of the nucleus. It's an incredible way to measure something that's almost impossibly small.
So, from one simple rule, opposites attract, likes repel, we've built a framework that explains a floating sphere and even the size of an atom. The real question is, what else can we do with it? When you think about it, from the battery in your phone to the giant particle accelerators smashing atoms, the principles of electrostatics are the bedrock of our entire modern world. And it all started with the simple, elegant rules of the unseen architect.